And then I went to other place, and then with other friends, and they also asked about comments, and then I realized that I can really make some comments on it, and not because, I'm not an expert in movies in any way, so it won't be about movie, but it will be about story. And the story I think is interesting, and being a physicist opens some things about it, which I really want to share with other people, and I did already at several languages, but every time the story is different, what I find out. So today's story, there is on YouTube the version in Russian and in English, but today will be different a little bit, because again, it's a story, so it lives. So first few words about physicists, and then about Oppenheimer. So physicists say to think about everything from first principles, and we have different first principles, and you don't like this principle, we will get other principles, but there is one principle in which physicists more or less in agreement with chemists, and there will be a lot of chemistry in this talk. Almost all the people here, which I'll show you, being great mathematicians, physicists, etc., are chemists also. Chemical engineers, but their first education. Something which I discovered and was really surprised, and I'm thinking about many years, over and over, so you'll see. It's a principle of that what rules the world is a free energy. And the free energy is, it's written here, it's F equal E minus Ts, and E is an energy, and S is an entropy. And entropy is a missing information. So everything in equilibrium goes to the minimum of free energy. But if atoms of our bodies are in equilibrium, it means that we are long dead. So we don't want to be in equilibrium. So we need not to go to the minimum of free energy, but to be somehow up. For this, we need energy and information. So there are two things which essentially you can look at history from this perspective. So what we are doing, we're obsessed about energy and information. And what I find particularly interesting about this story, which I'm going to tell you, is that people who participated in most energetic event, man-made event in history, and people who more or less provided us with the energy for the foreseeable future, and people who started the information age and invented the word bit and created and designed the first modern computer, are all the same people. And most of them by first education were chemical engineers, and then there was some physicists and mathematics thrown in. And that's something which I find very, very, to some extent unexpected, very interesting, and movie is good, I believe. At least it sheds some light on it, which I find really interesting to comment. So what I think is our time in which we live is that we're kind of shifting our focus from being obsessed with energy, more being obsessed with information. And so let's see all these people, and this story really, of course, there's very difficult to point where it starts, from Becquerel, from Curie, from anything, but one really important historical point was when Leo Szilard, who is here, wrote a letter which Albert Einstein signed, and this was a letter which almost right immediately after the discovery of uranium fusion. Fission was about possibility to use nuclear energy, and it was sent to the president. And then it's a very natural question: why these two people? Okay, why Szilard actually came to Einstein, and Taylor was his driver of Szilard, and these two people met first time in Berlin. Again, the date, like nobody remembers, but more or less it probably was 1926, and that's how they looked at that time. Szilard just got his chemical engineering degree and started to do a PhD with von Laue, and it extremely disliked the problem that von Laue gave him. So he met at the corridor another professor, young professor, comparing to von Laue, Albert Einstein, and said that he doesn't want to work on this problem, he actually thinks that working about other problem. And he started talking, and in 5 minutes Einstein said this is nonsense, and in 15 minutes he said, okay, write a thesis on it. And then this conversation, the word bit was first used. That's more or less what I talked with Albert Lipschitzer, and he agrees that this more or less we can say is the beginning of information of age started more or less in earnest, and then of course Shannon and other people. So they knew each other, and they actually had few patents, in particular refrigerator. There is Einstein Szilard refrigerator. So the people knew each other for quite a while. And so they wrote this. And as you will see later, the other people who will be in this story were also very closely connected in this or that way. But the story about now, what comes is a main figure. Again, when historian or storyteller tells a story which is named Oppenheimer, which means that Oppenheimer you don't choose, it's already your protagonist. So what you choose are supporting actors who will be other people. And it's very interesting how Nolan chooses what other secondary characters will be in the movie. And the first important character, which then goes through all the movie, is Isidore Rabi. And this is scene from the movie. I just want to remind. What is really interesting, well, of course, Rabi was also got his BC in chemistry, he's chemical engineer, for sure. And then he got PhD in physics, and he is like a sidekick, he's a secondary persona here. Scientifically, Rabi got Nobel Prize, and Einstein did not. Rabi did things which much more important for the Second World War, not only he, but on American side, which is radar. Radar is immensely more important than nuclear weapon, of course, for the Second World War and for the rest of things. But here, he is a kind of second persona to Oppenheimer, and I really want you to see this way, and this also tells you to what line Nolan introduced in this respect, and also what we also associate with Rabi. He had many, he was a very smart Jew. He had very things. But one that he always said that his mother always asked him when he came from school, easily, did you ask a good question today? And this story which Nolan tells us is about asking questions. And we all know that science is about asking questions. Right? And in a sense, the central part, the axis of the story is about a question which somebody asked, and then somebody asked somebody, and this. So that's one of the things which Rabi is that important. And another thing is that, let me just show you this.
Точно все выяснили, я планирую. Я was speaking so much myself, screw you. It's the moment.
This is an important thing, and I really want to comment a couple of words about other side of the park. This is a guy from the Lower East Side. I guess everybody more or less knows the geography of Manhattan. And this is a guy from Upper West Side, which means that those are simple Jews. Those are like third generation, which is kind of also very important. So on their side of the park, Yiddish was not spoken. On this side of the park, the Yiddish was the main language. But at this point, what really appears is, first of all, orange. I really wanted to know what is orange, right? And Jewish tea, Jewish side of the story. And that's important, and that would appear, and Rabi appears several times, and I've checked more or less historically, it's very accurate. The moments where he showed to appear, it's very, very accurate in the story, even though the part of the movie is not accurate, and I think intentional. Some things which just show not the way they take. But what Rabi is really an important part of the story, and here is a big orange. This is a big orange. Okay? Again, orange, and I don't know, and I did not, I'm not a professional in movies, so I did not analyze all that Nolan said about movies, so I've never seen him commenting on the orange. Coppola, about his orange in Godfather, commented maybe 10 years after the movie, and we now know that in Godfather, orange play a very important part. It's death. Everyone who touches oranges in Godfather dies. Who looks at it get, almost assassinated like the old victim. So, but I'm sure that the fact, and orange appears also later in this scene. And of course, orange is really something, this is an implosion device, and a little bit later I'll explain the physics of it and why it was so important and so crucial for the whole story. But I think that visually, Coppola explains that for them, orange was needed like a bright spot in an otherwise dark New York scene. And if you look at the previous, you could also see, this is a pretty dark scene, and there is this orange which is in his hand. So now also this story about this design is something which really explains, because movie over and over returns, why Oppenheimer? Why this theoretician, which was unheard of, a Jew, which is, a Serbian which will appear in a moment, was not taken into Berkeley after they did the bomb. They said, one Jew is enough. We have Oppenheimer, 2 Jews would be too much. So really, Oppenheimer was chosen, and in a sense, he have chosen himself, because first of all, he started to think about the bomb design when everyone else was thinking about, isotopes and how actually to get uranium-235. And second, that he really convinced Groves that the way that need to do science was totally opposite to what Army or any other project did, decompartmentalization. He says all the people who was working on this thing need to get into one place and talk to each other freely. And that was again, is head of the Groves that he agreed to it. And when they get together, Serger, which also will appear later in this story, Serger started to give all the people who get there a primer. A primer was just explaining what they already knew and what are the problems. And they were listening. And while they were listening, this guy who is over there, and I will sometimes show how it was in real life and how it is in the movie, just to see. And they're very accurate work done, actually, by Nolan. So while Niedermeyer heard this primer by Serger, he asked the question, he says that why, at some point Serger explains that our idea is that you need a critical mass. So you take two pieces of uranium or plutonium and shot one into another, or shot them together. And immediately the question that Niedermeyer asked, why one-dimensional? Why you need it along the line, right? It's kind of, why don't you do it differently? And then at some point, and that was I really vindicated because I did not know it when I first started to talk about oranges, but quite recently I discovered the words of Niedermeyer. So I thought about orange. You want to squeeze orange isotropically, spherically, if you want to get the juice out of it. And so the most important part of the problem that physicists were solving, not chemists who were dividing isotopes, was how to compress things isotropically, which is called implosion. And that's a design, this orange design, which I'll later comment how they came to it and why they came too late and how many millions would be saved if they came to this. This is of course a story of it's a very dramatic story. But this is really orange, and I think that no one put this orange intentionally. And if this orange would appear again. So now just to get a scale, this is a scale. That's a $2 billion, which was the whole auto industry of America. Probably quarter was wasted totally on which, again, I don't really want to, it's beyond, it's more about Lawrence and Oppenheimer, but still it's enormous money and it's enormous effort of many, many people. Instead, I want you to ask questions all the way, right? So I'll sometimes stop, and if you want to ask any question, you ask questions, okay? Because there will be some things which maybe I'm not explaining well enough, but I'll get to some physics. Those words in the movie, he really said it, and we have Rabbi commented on it, and maybe I get a little bit ahead of myself. Rabbi extremely disliked, they were very close friends, and he liked Oppenheimer very much, and he considered Oppenheimer the best physicist of their generation in America, and he thought Oppenheimer much, much better than him as physicist, and he liked him as a physicist, but he extremely disliked how he behaved after the explosion. It was something dark, as Rabbi said, and in particular this Mahabharata citation, which was true, and we also know it from Rabbi, from Beta, he disliked. So okay, so physicists watching, and of course they are watching Hans Beta, this is Hans Beta, that's Fermi, that's Feynman, that's Serger, which I already showed, that's Oppenheimer, Bradley, who was a director, Taylor, Bright, so there are kind of all the people. And what I'm showing you this picture is just also, this is Feynman, Coulomb, which appear later in the thermonuclear story, Fermi, Rabbi, Lawrence, and when you look at the scenes from the movie, some of them are like recreated photos, which I find kind of very beautiful. So there's really some work put into it, this Feynman did. And so now, this is again comparison with how it's done. So now I really want to ask the question which I think not very often people ask about it, and of course which people in the story ask over and over, was this success or failure? As you remember, they started at 39, and there was some kind of Uranian committee, and there was some very, very slow progress, and they get a financing, $6,000, and Fermi and Siller started to build the first reactor in the basement of Columbia on some private money. And then again, it was the people who started it was immigrants from Europe. And they did not really understand that American physics worked differently. Most of the money were in private grants, not in government money. It took a lot of time to sort all this out and to get everything together. And so they started kind of slow. But then they really wanted it by the summer of 44. And it's really important, and here I just put some, these are their photos from their personal files. So this is how they look like. This is Ulam, Fermi, Segre. I just want you to remember this name because in a moment they appear really different. Here's Vicky Weizmann, who was a CERN, Rudy Paras, who did the first, he was a British, of course they were German Jews, right? And Plachik, Czech, and Fermi, Italians, and Russian, and Ulam from Poland. They were all immigrants, so of course what they cared very much about was the war in Europe. And particularly those people, I also put von Karman. He was not in the nuclear project, so other important Martians. These Hungarians was called Martians because they were supernaturally smart and spoke language which nobody understood. And in English had an accent which nobody can imitate. There is a lot on YouTube, for example, of Taylor of later years. I think I watched it all. It's unbelievably interesting. It was very difficult to get through his thick Hungarian accent. Budapest Jews were started to be exterminated at the end of summer in 44, right? And so this was, if they were in time for the summer of 44, Russia took Budapest, I guess, in December. Wheeler, who is not shown here, who was boarded a droplet theory of nuclear, Wheeler estimated that being late by 1 year costed humanity 15 million lives. And so more or less that's what they all felt. So I really want you to feel what these people felt. So they came from there, they participated, sorry, which one is this? Okay, sorry, it's mine. And now one may ask why. Did they do any mistake, error, dead end? And so in a moment I'll show you how other teams made these errors. What was the problem actually which they...
Misha, I just want to say that I personally know half of these people on this slide. So
yeah, I agree very much.
They know.
Almost all of them people whom I admire in this or that way, including Taylor. The problem were two. There were two ideas of a bomb. One was uranium-235, and this is something which is a very rare isotope, so you need to get it, and it was a very, very difficult. This would actually cost most of this $2 billion. And Groves made a critical mistake at the very beginning by going with Lawrence into his direction. It costed half a year minimum, and so all the direction which actually worked afterwards was postponed. Even though scientists recommended this. So there were mistakes made not on Los Alamos level, on other things. So, but Los Alamos did their job very fast. By 44, the design for the gun was made and it worked perfectly. Because the problem is that the moment you start two parts of uranium approaching, they start to create a critical mass. So over here, neutrons from here get penetrated there and start hitting this place. As they start hitting this place, they produce secondary neutrons. First of all, there is a shock which throws them away, and second, there is this other material which appears after this reaction. So the thing is that you need to shoot this very fast. Fast enough so that it is faster than the time by which it can get kind of self-destroyed or fizzle out, as they say. This problem they solved, gun worked. It was actually already shipped into Pacific and waited for uranium to fill it, and uranium was not there. And it just took another year another 10 months to produce enough uranium.
And uranium they did in Oak Ridge, right?
They did it in several places, but in Oak Ridge they did this electromagnetic thing which lowering the site, and this was a bad way. And what the chemical diffusion way and centrifuges, which they actually postponed for even later. There were 3 ways, and they used least effective of them. Okay, and so they were coming, but coming very slow. It was coming. They already get enough amount to do all the measurements they needed, but it was not enough to get the weapon. Moreover, they were so sure about this gun design that they did not even test it before using it. Plutonium was abundant because plutonium is something which you get out of uranium-238 in a natural reactor which already Fermi, Wigner, and Siller built in Chicago. 42. It worked. It worked, and it produced plutonium with a constant rate. They had enough plutonium. The problem was that they got real plutonium in their hands, which was produced in Chicago. They started to measure its properties, and they found out experimentally that when plutonium started interacting, it produced much more neutrons than they expected. You know, nobody knew cross-section, nobody knew how fast it would go. That was really a very complicated computation. A little bit, I'll tell a few words about it. So when they got real plutonium, they realized that the gun would not work, as Niedermayer said back then when the Serber gave their primer. Niedermayer said it would not work, we need spherical thing. Because in this, there is always can get this, but when you get spherical, you also squeeze things. And this is here what you really can appreciate the genius on Oppenheimer and how he worked. He thought that this is nonsense, but there could be something to it. So back then, in 1942, he set Niedermayer apart and said, work on the implosion. You need something, you ask for it, work on it. So all this time, Niedermayer was really working on the implosion because at that point they realized they have enough plutonium, but they don't have, but the gun would not work because this was too slow. You really need to squeeze things. Okay? So that was situation for the spring of 44. And they succeeded in 10 months to create by total ingenuity. I mean, so this orange that you see there, it's unbelievably complicated layered thing. Most of these things actually, which I'll be talking about, it's about this thing, how you can do this. And you can immediately recognize the problems. At the moment you start to squeeze something, it's getting unstable. It starts, going into this direction. So you squeeze it here, go here. And this is really a problem which they solve. And then you can ask, okay, let me just is the water. And now I really want to see this angle from which Oppenheimer talks. And this is a photo of, I think, 1932. Nazis not yet in power. And this is Werner Heisenberg and his students. And you immediately recognize here people that you have seen in these personal files from Los Alamos. You see Placzek, you see Piers, who of course was not in Alamos at the beginning, but then he came from UK. You see Felix Bloch, who was his first PhD student, and Vicky Weizmann is here. So all this, and there is another person here, Vic, is physicist among us, know Vic's theorem, which we use over and over. So he was a very good theoretical physicist. Actually, after Fermi left, he was like considered, and Krakach left, they were the same age with Krakach. He was like the best Italian theoretician over there, but Germans did not want Italians, so they were kind of, German physics was the best in the world. So all these young people went to Los Alamos and did the bomb. So what did the Germans wrong? And that's something which unfortunately not very well known, even though it's kind of already was published in 1997, I guess, or 96. And I remember when it just came out, I stopped working, I just spent a week reading it. And that was what is called a farm hall transcripts. So immediately in May 1945, Americans went and arrested, interned all the German physicists of more or less of some stature and put them into this farm hall in UK. And they had newspapers and they had radio, and of course they've heard about Hiroshima and Nagasaki, and they were surprised. And what was published was the recording devices, which was put in every room. So they did not know that they are recorded. They didn't even suspect, one can judge by what they were saying to each other. And it's unbelievably interesting. I remember this feeling, for almost 30 years, reading these transcripts. And they told to Heisenberg and said, no, it's impossible, it's a hoax. These Americans just fool the whole world. Because this thing must be 2 tons. You cannot put 2-ton bomb into the plane and drop it. And later, this is a conversation which is kind of joined. There were like 5 or 6 people in this room. This is during the supper. But then Hahn, a very decent man, you can guess from all these records, and Heisenberg went to a separate room and asked, where is the blackboard? Hahn asks him how you do the estimate. And then you hear, and any PhD student at Weizmann would be shocked to hear how one of the greatest physicists of 20th century explains to Hahn the wrong, 2 orders of 1.5 order of magnitude, wrong estimate of a critical mass. And essentially what Heisenberg told Hahn is that you need to look at this neutron as it gets out, and then it gets out, and then you just need to estimate how, when he gets out, it will give you a size. Essentially he estimated mean free path. He assumes that kind of random walk model, assuming that not taking into account that there are 3 things. That it could be absorbed, it could be produced more neutrons, and it could be just scattered. So you need to know 3 cross sections, which are probabilities of this, and then you need to compute an average outcome, and not what happens to any single neutron. In the morning, he wake up and gave a right estimate. I mean, which, at least for me, I guess probably Pyrrhus said that he was a great physicist, but not a good one. This was, I don't know. But in the morning, Heisenberg, of course, thought about it again, and so you've seen this Dibner, also Bothe, whom Oppenheimer mentioned in the clip. That
Can you go through again slowly? What was wrong? What argument you used and what was wrong?
What Heisenberg essentially estimated the mean free path of a neutron, again, very roughly, and he got some size, which I don't remember, which corresponds to like 2 tons. It was pretty large size. What actually happens, the sum of neutrons, of course, go out, but it's just a minority. What's really important is that the neutron would get and split the atom and produce more neutrons. So the fact that some of them goes out, okay, but some remains. So we really need to compare this. It's not very complicated kinetics, for God's sake.
But Szilard patented the chain reaction in the 30s.
Yeah. But Szilard patented the chain reaction in a pile which constantly working. And it was working on slow neutrons. Maybe I need to say a few words about Szilard, who was not only the guy who invented beam, but the guy who invented actually the first, and patented the first reactor. And he actually explained, and I know this place in London where it actually happened, it's I've kind of, for me it's memorable place. He like tried to cross the street, it's not far from the British Museum. Then he stopped and then returned. And he was a chemical engineer and a theoretical physicist. That's why we call it reaction. It's all chemistry was for him. He thought about chain reaction 4 years before splitting of uranium. He thought about beryllium, but anyway, the idea of him was this, that you get more neutrons out and they would produce this chain reaction. But now the question is, but what he was thinking about is about slow neutrons. So how a reactor works. You get these neutrons out, you slow them down, and they don't go out. And that brings us to the second critical German mistake. Again, for a person whom Oppenheimer mentioned in the clip that I've shown, Walter Bothe, who was a Nobel laureate and one of the best experimentalists in Germany. And of course, they were trying to use different materials to slow down these neutrons so that they won't escape, right? When you do reactor. A bomb, you don't put there anything slow. Everything goes fast. So bomb is about fast neutrons, reactor is about slow neutrons. To slow neutrons, you need material. And everybody expected graphite to do this. And bottom measured it and say it would not work. And nobody ever checked it and corrected it. And of course, when Fermi and Siller started to do the same thing in the basement of Columbia, they found the same thing which Potter found. It does not work. But Siller was a chemist. He knew that there could be different purity of graphite. And so Americans in half a year created a very pure graphite. Just, somebody paid the money and they got it.
How did they come to graphite? Why graphite? Why graphite? What is the logic for choosing graphite?
Good question. I think that
we are talking about something that we know it works, but how did they arrive at this material?
it's about the nuclear of C.
Of the cross section of
It's
the
carbon, graphite is carbon. It's probably
Yeah, it's carbon. It's something about the nuclear of carbon which make it effective.
But why graphite and not just
Hold
coal?
on, hold on. Heavy water also do it. There are many different things, but at least when they were expecting graphite to work, just for the configuration of the nuclear. The problem was that there were other usually elements in graphite which were kind of changing this. And Siller knew that it actually forced a chemist to check it, and they did chemical analysis and realized what kind of impurities were harmful, and then they got this reactor working. Yes?
Comment and a question. So a comment for the biologist, it might be interesting that Szilard also invented the chemostat, and I think it's not coincidental, the chemostat versus the nuclear reactor. Both are autocatalytic in a sense. And the question is, what was the role of computation in estimating, like the Americans used computers, to estimate the critical mass, and the Germans didn't have? Is that a thing, or?
Good question. So first of all, the first thing, about Szilard I can talk like 10 hours non-stop. So Szilard also, when he got cancer at the age of 60, he devised the first radiation therapy for himself, and cured himself. This was the first radiation therapy. Szilard was I think that Szilard much more deserved movies than Oppenheimer, and such movie will be done in opera, I don't know what. And the second question, on this estimates, etc., in a moment I'll show when Oppenheimer come to Einstein, you see, the first report, there was just 10, 12 pages. Computation was started to be important when they started implosion. All the reaction, all the kinetics like this, Gans better did it. You don't need computer when you have Gans better, you don't need computer. But it's really important to understand that there were many dead ends, and people in Los Alamos did not fall in any hole. They just went more or less right. But they work in a way which nobody worked ever. Like everyone can get. Somebody, I remember some young, not Feynman, he wrote that I came to a place where there were people of whom I've read in textbooks, and I can ask any question and disagree with them just violently. That was an atmosphere which usually do not exist even in universities, even though Szilard, of course, was, Szilard worked in the first institute. Weizmann Institute is the third institute in the world, right? The first institute was Chris Haber Institute, and Haber was director. As Szilard was a PhD student, and Haber used to say, I am a director, and he is the general director. Because Szilard was going and telling everyone what to do. He said to this guy, you need to invent electronic microscope. He says, how? Okay, you'll figure it out. Now, really I'm coming to what kind of a central piece of this, which kind of reappears over and over again, this kangaroo court, which they did in 1954. After Oppenheimer was kind of the most famous physicist in the world, and definitely in the United States. And this is the first time that this appears, this is the word H-bomb, and what I really want to tell you, and which I think Nolan really understands very well, and which I'm not sure that very easy to understand when you watch a movie and you aren't a physicist, that this movie is actually not about nuclear. It's about terror. At least most of it.
About?
Thermonuclear weapon, which is H-bomb. H stands for the hydrogen, and of course it's not really a hydrogen bomb, it's a much more complicated thing. So now let me just show you, that's the beginning of the movie, the very first minute.
Dr. Robin.
Now,
dropping.
You see, it's fission.
And as we begin,
And then when you look here, you'll see.
Stop dropping.
No, it's unfortunately. Okay, let me just let it go.
Stop dropping.
So that I'm not sure many people noticed this appearance of these words. So the moment that Oppenheimer appears, there is the word fission, and the moment that Strauss appears, there is the word fusion. And this is a thermonuclear reaction, and this is a nuclear reaction. Fission is when uranium breaks into two parts, and fusion is when two hydrogen or deuterium, or as we later see lithium, fuses into one atom. Okay? And in the very first minute, he actually sets what is the main theme, but again, he doesn't insist on it. Namely, there are many different stories here, and this is, but I believe that this is an axis of this film on which it is actually made moving, and that's a second part, which is in the.
Tell me. What do you
That's a scene which is total invention of Nolan. It never happened. And people from advanced study, which I mean, I worked for a while in advanced study, also in Los Alamos, doesn't make me an expert in it. Our beloved pond was not there at the time. I think intentionally he made it with a pond which was not there, and the conversation which never happened. And the moment that Oppenheimer actually went with this Taylor computation, he went to Compton and not to Einstein. But I think it made intentionally, and it made it to kind of raise it into the level of a central theme of the movie, which is about the unexpected logic of research, in which I think why it's interesting for scientists to look at it and to see it. And what question asked Oppenheimer? And it's a Fermi question. And Fermi question is something which for physicists is a very, very specific thing, but I want to show you another clip where it really appears in the movie.
It doesn't go off. We're both finished. I'm getting on 3 kilotons. If you ask what get is, what does Fermi mean by atmospheric ignition? Well, we had a moment where it looked like the chain reaction from an atomic device might never have stopped. Chain fire to the atmosphere. Well, why is Fermi still taking side bets on it? Call it gallows humor. But are we saying there's a chance that when we push that button, we destroy the world? Nothing in our research shows that supports that conclusion. Except it's the most remote possibility.
So Fermi question is something which is totally unexpected. It needs to be answered without doing a big research. Something that you can kind of just estimate. This is an example of Fermi question. This probably, where is everybody, is the most famous Fermi question. You know what it's all about. It's why we don't see extraterrestrial life, because he just did a fast estimate and it seems that it must be everywhere. And so Fermi asked as early as 41, and we have a very vivid description of Taylor, how he did it. So what if you just do nuclear explosion of uranium, and the nitrogen in the atmosphere, 2 atoms of nitrogen would come together, and there is so much nitrogen that of course it could go over and over. That was a question for which Taylor tried to answer, and then they found a mistake and in Taylor computation, and then Bethe took into it, and nobody could do better than Bethe, and then more or less there were 10 minus 7, 10 minus 6 probability. The problem is that they did not know cross sections really, they just estimated it. So they were trying to assume that they were making several steps, and at each step there was an error which they don't know, and that gave them an estimate of probability. And that was still very low. So more or less they were almost confident. But really what is important here is that I think that in the movie it's over dramatized. They weren't really, of course Fermi was a cool guy, so he really took bets at the night of test, on it, and they were betting. They were also betting on how many kilotons will come out. They were young people, and but he really made it a point, and then, I mean, there is the beginning of this conversation with Einstein, and then the end of this conversation with Einstein about the unpredictable nature. And the unpredictable nature expressed was in following. Then after that, Fermi asked this question. Teller was absolutely obsessed with it. He worked for a while, but then when Bethe was made a chief of theory division, he only thought about it, because if this is possible, if you can do it, then immediately he realized for nitrogen it's too difficult, it's too large atoms. But you can take hydrogen, or deuterium, or lithium, some light elements, and they would really, because what we call Coulomb barrier, the electrostatic barrier between two nuclear is not that large for small nuclei, you can really fuse them together. And then, what I really want you to see, what physicists see behind this. These curves are how much energy per particle in the nuclear they are. So this is the ferrum over there, the iron, which is the most stable element, right? Because you just cannot get there. Here, uranium is over here, right? So when your uranium split into barium or something, then you get that much energy. That's what you get from nuclear fusion. That nuclear vector. Now, this is this side. There are light nuclear. This is hydrogen, deuterium. Notice this minimum. This minimum plays a big role in the history of mankind. So when you go here, you know, like from 4 to 8, 2, 4 get you 8, you get from here to here. That's how much energy you get. And that's a picture which is essentially was in the mind of Fermi. They did not know details, and the many numbers here were measured later. But this is essentially what, from a physicist viewpoint, what it's all about. It's about this curve. And then they were actually asking, can you get into it? So when you look at it, and when you understand why at the beginning of the movie we see Oppenheimer with the word fission and Strauss with the word fusion, and why this kangaroo court was just happening at all, you understand that it was this big puzzlement all over why in 1942, 43, 45, 46, 48, Oppenheimer was consistently against H-bomb, what they call super, this project, which Taylor was pushing, and they were totally not, again, the question was the same. When we tried to do it, there was so much energy release that they would go out without actually reacting. So again, it was a problem about implosion, how to make this implosion really this way, and nobody could realize it. And then at some point, you remember this court, this security hearing, there was 54. By 54, there was already explosion, and the next year, and there was already Russian explosion. And so people in Washington was really puzzled how it could be that what Oppenheimer and in a moment I'll comment on Landau in Russia, was impossible in 3 years, we're just here. And this is something which I really want to comment, because what happened is not that Oppenheimer was kind of wrong or disloyal or whatever, is that the people who were really geniuses invented things which did not exist before. And they invented it because, you know, again, this question that was asked, and then to the next question, and I think the most important person here was Star Ulam, who invented this, and here you need completion. That's where, you know, because von Neumann did unbelievably beautiful, it's essentially all about hydrodynamics, but complicated hydrodynamics. With radiation pressure, you know, it's kind of, but still, it's a flow. And so Ulam invented the idea of stage implosion. Namely that you do something which is very, very carefully staged. So you do several explosions, it's a multi-layered design. Sakharov, who was 27 at the time, and he was a genius. He started to do quantum hydrodynamics in 1947, and if he would not, in the right direction, as we know, if he would be taken to this project, he would really do great science. He also did great science. He did more or less alone with Ginsburg what these three people did, and without computer. which von Neumann had. So they already did the advanced computation at 5051 using the computer. And that was needed because they needed to suppress instability. The moment you start squeezing, it starts going here. Right? So you try to squeeze it, it goes out in jets. Right? Because it does not want to stay spherical, right? The moment you disturb sphericity, of course, in this direction there will be more pressure, in this direction will be less pressure, and it will just go. So there was a very complicated geometry which you really need to do, and for this you need a genius. Who was also a chemical engineer, but his first education is simply. And the reason is simple. Physics was not a profession when these people grew up at the beginning of the century. Chemistry was a profession. Or mathematics would be, you could teach in school, but physics was not. So at this point, they really needed this computer, and it was invented. And I just, to see you the title, you see that the electrolytic reaction, hydrodynamic lenses, and radiation mirrors. That's what it's all about. And that what allows these people to create the most energetic event in history. And again, Oppenheimer was very much against. And there is, maybe I'll just show this a very short clip. Here, I just comment for physicists, I have like 6 minutes, so I'll try to be short now. I see curious parallel between Oppenheimer and Landau as they started at the beginning. Two Americans went to Europe and learned quantum mechanics. Oppenheimer and Landau were two people who knew quantum mechanics in America for a while. There were no other people. And Oppenheimer created the whole generation of people, educating them, and Serber actually wrote a kind of informal textbook. And Landau, of course, did much more. He educated many generations of physicists by creating his course, but this was more or less the same thing. And there are other curious things. Landau got not his trial, but his 1 year in jail. There are interesting parallels, but what is important is that both were strongly against working on nuclear weapon. On things which, and it was very, for Oppenheimer, it was, he paid dearly for this, but kind of not in jail. Landau was very indirect, but we know from Sakharov memoirs that Landau at some point, and he was very young, Sakharov, and Landau was kind of, famous. He took it out of the building, which was very unusual. Comes here as a big academician and takes a young student, postdoc, out of the building and start talking to him that maybe it would not be a good idea to go to Zeldovich, to this Los Arzamas, as they used to call it in Russia, and work on this project. And Sakharov, being young, he understood it much later. He writes in his memoir what it was all about. Landau was trying to tell him, and he was asking naively why. And Landau, of course, couldn't explain why. So he just stopped at this. So there is kind of this curious parallel between these two people. And now looking back, because they thought this idea that Landau had and Oppenheimer had, that government uses everything that they use. Still nobody used thermonuclear weapon. And that was actually Teller claim, that thermonuclear weapon guarantees that Third World War between America and Russia won't happen. And it did not happen. So I don't know, I'm not here working as a historian, but I just want you to see that there was a really big question. And then these people went and created this weapon. And the last thing that I want to tell you, how actually the same person and the same people solved the energetic need of mankind, which is a controlled thermonuclear reaction. Because there is as much water as you around, and not much uranium. So nuclear energy is finite, and thermonuclear energy is practically infinite. And the first idea to work on it appeared very interesting. There was a sergeant in the Russian army working in the Far East who sent a letter to Moscow to the Central Committee with an idea how to make controlled thermonuclear reaction. I guess it was 48. And they gave it for expertise to Institute of Physics, and Sakharov was there, not yet working on nuclear, and Sakharov was there as a young, just fresh PhD, and they gave him, and he wrote a referee report on it. It's beautiful to read it. And of course it was a wrong idea, But the whole idea strikes Sakharov as very original because everybody was thinking about compressing things. Because they were all thinking about bombs. For uranium, you don't need it. You just mix it and you slow neutrons. If you want thermonuclear reaction, that you really need to compress it because it just kind of blows up. And his guy was talking about gas, plasma, right? Ionized gas. But this is very rare. You know, the collision between atoms happens very rare in a gas. It's very dilute. So the idea was that you need to heat it so that they really can come fast and hit each other and overcome the barrier. But then, kind of when you hit it, it just go up. So the idea was to heat it and keep it. And it's called Lawson criterion in plasma in thermonuclear physics. And this guy Labrinka, he suggested some configuration of electric fields which was unstable, and immediately Sakharov realized that this is unstable, and he wrote the report that it would never work, and he continued thinking about it. And the same very year in which he invented the first workable design of a Russian thermonuclear weapon, he invented tokamak. And tokamak was the idea that you just take a bagel, you take a torus, and you run current into it and you put magnetic field. And this magnetic field, it would work like this. It would make electrons go around and not, escape into the walls. So this way you could really keep this plasma. And of course, many years later, and for example, when I was a grad student, I was in plasma group, and then I decided this is a hopeless project and went out and did fluid mechanics for the rest of my life. But it works now, in a sense that was so many technical problems on the way, but essentially that's what we got out of all this. So, in a sense, what I finish this story is that it's interesting how, for me, this movie is about not only this, of course, about human drama and a very interesting personality, but it also shows unbelievably interesting people. There are many people appear there. They don't bear, name tags like I'm Fermi or I'm Siller, but they are there. If you know that this was Siller who came at this moment and asked him to sign petition, and this is Fermi who was, making bets on atmospheric ignition, and there's these people. And also, I think it's really about this unpredictable logic of research, which you ask question, then you ask question, and then you ask question, and here you are. So that's the whole story.